Okay, good morning, everyone, and welcome to SpaceGeekSpeak. SpaceGeekSpeak is a Houston, AAA Houston section morning program for every Saturday we get together. And when sometimes we have fantastic speakers like today, Edmund will be presenting on engineering of the lunar lunar building. And so it's very appropriate and timely as we are working toward establishing our presence on the lunar surface. And so I invite Edmund, this is your time and to share your knowledge and historical perspective. Thank you.
Okay, yeah, I'm going to talk a little bit about, this is a trip down memory lane, history of a NASA program. So in the beginning, there was what was called the 90-day study that was done at Johnson Space Center. And this was an attempt to look at what should be NASA's next step after getting the shuttle flying again after Challenger, and then the beginnings of the planning for the space station program. And this was turned in, and then a big effort was done inside NASA, and it became the Space Exploration Initiative, which was under President George H.W. Bush. In the upper left-hand corner, they put out a nice glossy book about it. It's available for download off the web. I don't have the URL, but it is available. But this was released in May of 1991. And if you look at the chart on the right, this is a very, very ambitious program. The space station Freedom was going to be evolved into not just a research outpost, but also as a staging point for missions to the moon and to Mars eventually. They were going to build a whole series of new launchers, a cargo version of the shuttle. They would use the Advanced Launch System, which is under development by Department of Defense. And then going on to more heavy lift vehicles, there were going to be developments in nuclear surface power, big upgrades to the telecommunications and comm systems, setting up facilities on the surface of the moon, and eventually going to Mars. And Freedom at the time had planned to be three components. There was going to be what we see as the International Space Station, but there was going to be a free flyer in a trailing orbit that was going to be used for microgravity research so that crew activities wouldn't affect the microgravity. And there was going to be a orbital transfer vehicle to move that free flyer to and from the space station so that it could be berthed to the space station and equipment taken in and out, samples taken in and out. But as you can see, about halfway down, it was going to have like basically docking stations for reusable transfer vehicles. So the budget in 1991 was about $14 billion, which is $35.8 billion in 2025 dollars. The estimate on the cost of this was $500 billion over 20 to 30 years, which would have bumped NASA's budget to $17 to $25 billion. And that was $1.3 trillion in today's dollars with a NASA budget of $40 to $60 billion. That was pronounced dead on arrival in Congress. It was the nickname it was given was Apollo on steroids. This was a time of great budget pressure. If they increased spending on a discretionary program that NASA was part of, they would have to cut spending elsewhere. So this was not going to fly. So after this was rejected, NASA retrenched into the First Lunar Outpost. And I'm going to talk about my view of the First Lunar Outpost as being one of the low-level grunt workers on it. So I say, this is how I learned lunar dust is not your friend. So in 1991, I was a support contractor with Lockheed to Software, Robotics, and Simulation Division, ER Division at JSC, in the Engineering Directorate. So they were asked to put together a team to look into automation and robotics for lunar base studies that were being done with the Exploration Programs Office. And we had two senior NASA staff, one of whom had worked on Apollo. And I was brought in because I was a software developer and had done work on automation and robotics in my time at Rice and in the work I was doing for ER. One of the things I did was Space Station had a reliability program, software program that did Monte Carlo simulations of equipment failures, and I used shuttle and space station reliability data to come up with what would be the equipment in a lunar base and come up with some ballparks on what the maintenance and logistics needs were going to be. And we wanted to use this as an input to robotics and automation concepts for the base maintenance and operations. As an aside, one of the big things that you have to have spares of back then were light bulbs. Even fluorescent tubes burn out. They eventually had a lot of problems on space station with the fluorescent light fixtures failing and not having tubes on hand. So they were actually moving lights between modules as needed. So I also did some studies on landing success versus rock size distribution. I wrote some software to generate rock fields, did Monte Carlo landing simulations, both direct vertical descent and then also with some side slip to give you probabilities that you would hit a rock and damage the lander. Went to a lot of meetings in TIMS at JSC as we were exchanging information, including a big one on lunar dust, where I learned that it's pretty much the worst stuff in the world if you want to have equipment, particularly moving equipment, because of the composition of dust. So in February of 1992, the results from all the initial studies was what was called First Lunar Outpost. And these are, I was given, after these meetings, I was given Xeroxes of the slides, which were, the old view graph foils. And so they're a little bit askew and kind of fuzzy, but I scanned those in for this. So I'm going to go over what the concept for the mission and the design guidelines that we were given for developing what the initial concepts were. So it was going to be a pre-integrated man-tended outpost that would be landed on a cargo lander. And it had facilities for a 45-day for a crew of 4, giving you a lunar day, night, and day cycle. Would allow consecutive crew visits. The lander would be on its own flight. The crew would come and land next to the outpost, which had been checked out remotely. The lander would be powered down, except for heaters, stay alive heaters and cooling during the surface day. And this way, the budget was very, very key in all this. So they didn't want to have the upfront cost of having to prepare a bunch of infrastructure ahead of time. They wanted to use existing hardware and components and systems whenever possible to reduce development cost. And as in all systems engineering and trade studies, you have to trade off cost, schedule, and performance penalties to come up with a solution that meets what you're trying to do. They assumed that there would have been unmanned landers to characterize the landing site. And one thing they were going to have to develop was automated landing for the cargo missions. That's one of the reasons I did the study that I did, the simulations and calculations. And, to set this historically, when this was being looked at, the most sophisticated CPU you could get was an Intel 486 chip running at 50 megahertz with a few megabytes of memory. So the landing system was basically going to be radar with possibly some primitive image processing, but that was considered very experimental. So all the flights would be what they call lunar direct, which would allow the crew to return without waiting for a launch return window, unlike the initial plan for Artemis, where they were going to have the gateway and NRHO with Orion waiting, and they would have to have only a window of a few days every couple weeks. And this would also allow you to go to any lunar latitude and longitude that were of interest, and only one crew vehicle would be needed. And then again, to give the crew more time, reduce the surface operations required for activation, and optimize their time for science and in situ research, resource utilization studies. The flights, the human and the cargo flights, would both use the same translunar injection stage and the same lander stage. So we'd only have one of those to develop. And high energy propellants such as hydrogen, oxygen for the translunar injection and then lunar descent, and then storable propellant for Earth return. So it'd be UMDH, nitrogen tetroxide, and they wanted to avoid any cryomanagement storage on the lunar surface. So this shows a diagram of the launch. There'd be 2 launches from Earth to orbit, a rendezvous and checkout of the docking with the lander and the injection stage, fire to lunar orbit with the injection stage, either go into a low lunar orbit or possibly do a direct descent, and then the crew would be able to come back on a direct ascent to Earth landing. So again, translunar injection stage to LEO lander with the crew in it. Cargo and habitat landers would also use this design. So they'd rendezvous and dock with the translunar injection stage, go to the moon, probably enter a 100-kilometer orbit and land 1 kilometer from the habitat to protect from ejecta. And then they would do a direct ascent of the crew module to Earth after time at the base. Again, 4 days for the crew, 4 lunar day-night cycle. The habitats on the landers checked out after it lands. Science and engineering were to start within 24 hours. The crew lander would carry 2 to 3 metric tons of science equipment and a rover. 1 EVA by at least 2 crew per day. The rover would take them out to 15 kilometers from the base, which gave them walk-back distance. And a traverse would be up to 50 kilometers linear distance, and go back to the outpost every 6 to 12 months. The walk-back distance, in part, was chosen for how well they could get back to the base, but there was also concern about any solar events that could come up rapidly, energetic particle events. A lot of concepts were kicked around on how to protect a crew away on a roving mission. From that, one wild hair was, well, we'll send some explosives and some metal plates, and they'll blast a hole in the regolith, put a plate over it, and then crawl underneath it and huddle under there until the solar event passes. Because the kind of event they were talking about was relatively short duration. That's not practical because of how densely packed lunar soil is. But we were in throw out ideas and kick them around mode. Just anything, it was all very, very much brainstorming mode at the time. So this was expected to have the ability to evolve. So do the early missions where they characterize the surface with unmanned missions, and then possibly do a sortie without the outpost there to do some quick EVAs for a few days and then come back. That was going to be dependent on what they could reconfigure the crew module to do. But then the initial capability, crew of 4, 25 metric tons on the cargo lander, and do some demos of resource extraction. And then after that, these initial missions, a waypoint to either go to a new site on the moon, and do that, use the outpost as a construction shack or the core to expand the facilities for larger crews, more science, larger resource extraction, or do the outpost at its current capabilities, and then look at developing long surface roves and things that might be needed to support and gather information for Mars missions. So that was looked at what would be done downstream. So I'm going to go through some of the subsystem presentations that were done early on. We'll look at the heavy lift launch vehicle. It was a Saturn V, not shuttle derived like SLS, but Saturn V derived with a 3-stage core, basically stretching the first and second stage and adding liquid strap-ons. Solids were rejected because of the experience with Challenger. That was very much in everybody's mind. So it was going to have 242 metric tons to 100 nautical mile circular orbit, and then send 95 metric ton to the Earth, or to the Moon. And the vehicle would have the capability of having 4 liquid strap-ons. The strap-ons would have their own tanks. We're going to use the F1 engines that were used in Apollo, and the J2 engines in the upper stage, 2 upper stages. So it was very heavily Apollo based. 13.1 million pounds at liftoff, which is a pretty hefty size vehicle. And it had to fit into the VAB. So we're going to look at the lunar lander with the crew on board. So the cargo flight would have 27.5 metric ton cargo on top. The descent stage would use the venerable RL-10 engines. The descendants of those are still being used. The new upper stage for SLS, the Vulcan stage they're acquiring, uses a later revision of the RL-10. Very versatile oxygen, hydrogen engine, throttleable, very deeply throttleable. And it would have several of those, monopropellant reaction control, then GNC system, data management, communications. They were still trading fuel cells and batteries, obviously the fuel tanks, a thermal control system, and a radar altimeter. So very simple design, just to get that cargo module on top down to the surface. So for the crew, be a larger, kind of like Orion, larger than Apollo, carries 4 crew. Descent stage, again, the same one that we saw for the cargo. And the upper stage would use these storable propellant engines, have all the crew equipment, all the normal stuff you would see, parachutes, retro rockets coming down, the EVA, IVN EVA suits. So all the things you would expect in a crewed vehicle, such as we have with Orion. Again, it's fuel cell based and not solar panels. And this is one early concept drawing showing a slightly different concept for the crew lander. At the bottom center, you can see the crew member deploying the rover. And that odd-shaped thing at the bottom was a cargo carrier that would be come down on a cable you can see in the center that would have the logistics and science equipment as well as the rover. And one thing, big ladder to get on and off of the vehicle there on the front. Again, this was an early concept and just sketched out. It's done by Pat Rawlings, who is a fairly famous space artist that worked a long time with NASA. So the habitat, what was the habitat going to be? This was an early concept. You would have a HAB module with a radiator and solar arrays, fuel cells, and the other consumables. The HAB module concept was to build it possibly based on the HAB module for space station, possibly using some of the same life support equipment, and that would be, again, trying to reuse things that were being used on other programs so that it would reduce development cost and development time. They looked at using the space station airlock with the habitat. Be able to handle 2 crew on EVA, and it would have its own Eclipse thermal comm systems, racks for storage of the suits, so that was again one concept they looked at for this. Again, minimizing cost by borrowing something from somewhere else. And that shows you a picture of the habitat on the surface with the crew lander in the background, a kilometer away. You've got the solar panels, radiators deployed on top, comm system. So these are some later version images of the heavy lift launch vehicle they developed. You can see it's got this is the crew version with the fairings deploying, the liquid boosters. Informally, Comet was the name that was kicked around by some people for this launch vehicle. And this shows the crew lander and the base. Instead of those 2 vertical ladders, you've got a nice sloped ladder for the crew to get on and off. I presented this before at JSC, and one of the people there said that slipping from lunar dust on the ladder was actually an issue for the Apollo crews when they were trying to get back into the limb. But yeah, so there were a lot of nice, pretty pictures developed for this. So the site selection was Mare Smithii, which is on the eastern limb of the moon. It apparently is fairly interesting geologically for a near side feature. I got the sense that the far side for the geologists is a little more, and planetary scientists is a little more interesting than the near side. But again, they wanted to have line of sight to Earth, so this was the site that was chosen out of one of the studies. So we're going to look at some of the surface systems that they came up with. The unpressurized rover, 0.615 metric tons, fairly small. This was preliminary, and they said, well, this, as you can see from the box, this needs some work. But it was to carry all 4 crew would be able to ride on it, or you could have 2 crew with a trailer and an additional 400 kilograms of cargo on it. Or it could be teleoperated with a 1,200 kilogram payload, and 25-kilometer round trip, 50-kilometer without crew on board. For the suits, they were looking initially at hard suits. This is kind of similar to the Russian Orlan design. You come in through the back. And it was one of the concepts that was kicked around for a little while was to have the airlock be designed so that, in effect, the backed into a hatch structure where that hatch on the back was, and then they'd open it up from the inside. You would dock this back of the spacesuit to the base, and then they could open it up and you'd crawl back out, and that was to minimize lunar dust contamination inside the base. And that was considered extreme unsafe and not particularly practical. But again, a semi-hard suit was the initial concept, and they kicked around other ideas. I think later on they came to more of an Apollo style suit, and like the suits that they're using now. But this was, again, early on. And then I'm going to go over science and payloads now. This is presented by Dr. David McKay. He was for those of you who don't know, he was one of the principal investigators for the Apollo samples, and he helped set up NASA's astrobiology program, trained the Apollo 11 crew in geology, one of the major experts on lunar dust and in situ resource utilization, published over 200 scientific papers, and he was one of the patenters of the first ISRU design for use on the lunar surface. These were some of the packages that they wanted to send: geophysical monitoring, a solar system physics experiment. One of my professors at Rice in the astronomy program was a PI on a solar system physics package that was deployed on one of the Apollo missions. And when I was an undergrad there, we're still getting data tapes every month on solar wind data. And they ran a big program and developed. Every month they'd run the tape, get a bunch of plots out from it, look for anything interesting to dive into. A geophysics package for taking on the traverses, geology tool set, a lunar transit telescope. The transit telescope was a fixed telescope. It would just be set up, pointed to the zenith, and would be able to use to study whatever passed by within the field of view. That sounds very strange, but you can see a fair number of interesting things if you're just pointed in the right direction, even if you can't tilt the telescope. And then a telescope that could be tilted and pointed, a smaller solar telescope, the ISRU demo package, which I'll talk a little bit more, and then the science rover, the robotic science rover that could be deployed. So looking at about 3 metric tons of science and payload equipment. And there would be additional equipment inside the habitat as a small geology lab and possibly a biological sciences lab. ISRU was one of the big things they wanted to do. They were going to have an oxygen extraction unit, and you would bring along hydrogen and react that with regolith at high temperature to get water, and then you can use that either as water or you could electrolyze it to turn it back into hydrogen, recycle that, and have oxygen for life support. This predates the discovery of the possibility of ice at the permanently shaded regions, the lunar poles, and so that was the initial concept, was to extract oxygen from the regolith. A brick making unit to look at the possibility of sintering lunar soil into bricks for construction, and then a gas solid unit to try to transport and sort the regolith into the various components. Regolith has a huge amount of glassy fragments in it, along with metal particles and pulver and other types of rocky pieces. It's very sharp, very abrasive. But this transport and sorting would allow you to pull the different components that you want for ISRU versus making bricks into different bins and then feed that into your ISRU system. Yeah, one thing that was a major design consideration was lunar dust. The experience on Apollo was that it gets into everything, adheres to everything. It's very tough on seals. Rotating equipment is so bulldozer type vehicles are going to be very difficult to get to work for long times because of all the dust clogging all of your rotating surfaces. But yeah, ISRU, big emphasis along with the other geology and solar physics. So in April 1st of 1992, Dan Goldin became the NASA administrator, and he was the faster, cheaper, better guy. In March 1993, he terminated all of the human spaceflight programs for Beyond LEO work. Now, that was not because of his antipathy towards these programs, but NASA was under budget constraints. They were still in getting space station up and going. That was consuming a large chunk of the budget for the development of space station and eventual deployment. And so it was a budgetary thing. NASA was not going to get additional money. They needed to work with what they had. So shuttle and station became the emphasis, and LEO type work was deferred till after those programs were up and running. I went on, did expert system software inside ER with Ames Research Center, did some AI projects, did some systems engineering for shuttle and ISS hardware. And eventually I was part of Lockheed's proposal team, systems engineering team, on the proposal for Orion, and worked on Orion for a number of years, writing requirements specifications. As a funny aside, Dan Golden banned the worm logo in favor of the meatball. He did not like the worm logo. He felt that it was not that the meatball was much more emblematic of when NASA was a dynamic, successful organization in the Apollo program. So here we are with ignition. Until ignition happened, I was working on Gateway. I was the NRHO phase cross-program tested verification lead, working with HLS, EHP, and Orion, working with the landers, suits, and Orion program on verification of the interfaces with Gateway. But so we're pivoting into new work, and it's very exciting. And that concludes my presentation. So questions?
I have questions, but let Svetlana, when you give me the time, maybe others have too, but I have a lot of questions.
Okay.
Can I begin?
Hold on 1 second, please.
Okay.
And I do see one question posted by Rock on online. How would Surface Hub operate during the unoccupied periods? Were there plans to keep it in hibernation?
Yes. The idea was that they would just go into survival mode until another crew arrived in 6 to 12 months.
Oh, I have a question.
Go ahead.
Yes, what was regarded in the earlier days as the most challenging part to establish a moon base? And then how does that compare to the most challenging part of establishing a lunar base with the ignition program?
I think, two things were, aside from the budget pressures to try to do this as cheaply as possible, which is always a thing at NASA. Surviving the lunar night was considered an issue. Another issue was the managing lunar dust. If you look at the pictures of the Apollo astronauts after their EVAs, they were just covered in dust, and it was a real issue. They inhaled it. Harrison Schmitt actually developed an allergy to it after he came back. So managing dust and surviving the night. For the South Pole, you've got dust is on everybody's mind. Surviving the night, especially since the areas of interest are some of these permanently shadowed regions. So if you're going to have equipment that may be when they get down to pulling the ice out of the craters, they're going to have equipment that's going to have to be operating at extremely low temperatures for long periods of time. So there's a lot of ideas being kicked around for storage for heating to keep the base warm at night. And you've got the challenges that, again, a lot of the sites do not have you're dealing with, at the South Lunar Pole, the sun is just barely above the horizon, a few degrees above the horizon. So whenever you're looking in that direction, you've got the sun in your eyes. And Earth spends a fair amount of time below the line, out of line of sight. So communications, they're going to have to set up communication satellites in orbit to relay data to Earth and communications to Earth. And so you've got surviving the night, dealing with power issues, because again, you've got some of the areas you have sun on some of the high ridges, you've got sunlight nearly 100% of the time, but other areas, very intermittent solar power is available. That's why they want the fusion reactor for the lunar surface, or not fusion, fission reactor, nuclear power reactor. So that's the challenges they've got now. I saw a question on transporting equipment back, logistics back and forth. The rover, again, the little trailer on the rover would be used to transport logistics back and forth. There was one of the things that we looked at for robotics was, could we have a rover with robotic arms that could be used, for example, to swap out consumables tanks on the exterior of the base. And so if you could put, so if you were bringing up additional hydrogen, bringing up it for the fuel cells, hydrogen, oxygen for the fuel cells, you could swap out those tanks robotically. So that was a concept that we kicked around and came up with some very simple concepts for. Again, one of the challenges for a lot of this was teleoperation. There were studies being done to support space station on teleoperation of robotics from ground stations with significant communications lags, so that you kind of have to do start and stop operations with the robotic arms or whatever robots you're dealing with. So all of those things come in. Let's see what else we got in the way of questions.
There's a question from Dr. Dunbar about the plans for dust mitigation on both suits and entry into the habitat. And I just want to preface it a little bit that Edmund is talking from the historical perspective.
Yeah.
And I don't think he can answer what is the current plans, but
Right.
if he can talk about what were planned at that time, that would be good.
Yeah, there were it was everything from vacuums with HEPA filters on it to vacuum off the outside of the suits inside the habitat. We could send up, sticky tape to scrape off the outer surface. For some of the seals, one concept was to have the seals have removable strips that could be peeled off if the seal started to get too much dust on it, for like the airlock seals. The mechanical engineers vetoed that, saying that being able to pull off layers off of the seals was not really practical. So
I have
and
a comment on this. Go ahead.
So, and there was even, do we have to have the crew wear masks inside the habitat? For ignition, for Artemis program, it's a major research topic. They're looking at some electrostatic techniques to cause dust to not adhere. Because again, in addition to its small size, jagged pieces, it has a certain amount of electrostatic attraction during the to anything it sticks to. So it was really bad stuff.
I have a comment, if it is okay. One of the things we were studying is like the lotus leaf the water falls on the lotus leaf
Mhm.
and it kind of slides. So we were looking at chemical painting or something like that that will not let the dust stick to the
Mhm.
structure. And that's one thing we were actively looking at. There were other things also being looked at, uh, such as this electrostatic
Mhm.
repulsion. Because, uh, well, when my chance comes, I have to ask you different questions. But
Yeah.
I wanted to tell that I remember a project where these guys needed money to study the lotus leaf.
Okay.
What is on the surface?
There's a
Okay,
question, the
that
landing
yeah,
zone. Yeah, the initial concept was 1 kilometer distance between the cargo and the crew module. That there's a lot of concern about that right now. One of the major data gaps that Artemis has is how far the regolith gets kicked up by landing, the engines during landing. There's a fear that depending on the size of the engines and the duration of the plume impacts the regolith, that you could actually eject small particles of regolith that would enter a very, very low lunar orbit and they would come back around and hit your lander. So that's one of the big things on Artemis.
basically creating your own self-made micrometeorites right there.
Yes,
And
yes,
due to the landing. Yes,
yes,
I did see those studies. And
yeah.
there's a comment from Dr. Dunbar that
Huh?
as a thank you for responding to her question.
Huh?
And she mentioned that Buzz Aldrin visited her lab in Texas A&M and said that he could not brush off regolith. The
Yeah,
jagged edges, micron size particles became ingrained into the EVA suit external woven layer of the fabric.
yeah,
And so there's it is, I echo what Edmund mentioned, that lunar dust and the mitigation of lunar dust is a very high priority topic and extreme significant challenge right now for us to address during as we prepare to establish our presence on the lunar surface.
yeah. It's a big. It's. I would say that for everybody that's designing equipment, it's lunar dust, power, and thermal regulation on the surface are your top concerns for any design that you're doing. And getting the equipment to survive lunar night is going to be a challenge. Getting the equipment enough power and then protecting it from lunar dust.
Well,
We had people.
another challenge I would like to add to your
Yeah.
list is also communication,
Yes.
is establishing the reliable communication, because again, as you mentioned in the earlier in your talk, is that the most interesting side is the other side of the lunar surface, right?
Yeah.
The dark side of the moon, for us at least. But at the same time, it is not in line of sight for communication, and so therefore, there's going to be the balancing between the communication capabilities and the interest of the scientific community.
You mean the backside of the moon, not the dark side,
Yeah.
right?
Well,
Far side.
yes. The far side.
Yes. As an
Right.
astronomer, we called it the far side.
Right. Dr. Kumar, you had a question?
Yes, I have several questions, but what I will do first is, uh, Edmund, you said, I saw your first chart. It said edmund.hack@gmail.com or what?
Yes.
Okay. So my questions will make sense and I will be brief. We will not cover all that. That's why I wanted your email. I'll send you some stuff. But I wanted to tell you that after the exploration was abolished under Bill Hofstetler, I was responsible for new technology um, identification for the Mars mission. When it was abolished, Dr. Hantun M. Lafik called me and said, "We need a jack of all trades, master of none, and you have been chosen because the Congress and the Senate is saying, what the heck is all this happening? How does it relate to human needs?" So I got into that technology transfer area. So why did I bring that up? I had to do everything you guys were doing. I kid you not, because to find out if there is any intellectual property, that's all. So with that background, what did they do during the Apollo? What did they? They couldn't use, obviously. When I saw the suit of Dr. Schmidt, I mean, you couldn't go back in that suit. Was it one-time deal? They came back and just stored their suit, or did they
Yes.
do something
No, the Apollo suits were not
one-time
reused.
deal?
They were one time. I think they were custom fitted to each of the crew. The Apollo,
So
yeah, the
when it
Apollo
was
suits were, yeah, they weren't reused.
when it was when it had the dust, when they came back, they just kind of stowed it, and
Yes.
that's about it. Oh, you answered that question very well. I have several other questions, but as I said, I will ask only a couple of questions. To me, when you're building something, uh, the consideration is environment, radiation, for example, temperature, I could go on and on. So this happens on the earth. If I tell you to do something for Death Valley, it'll
Mhm.
be entirely different than if I tell you to do something for Alaska.
Right.
So, how have you been keeping up? Did we solve the radiation problem, for example, and the charged particle problem?
Um, they, yeah, there's concern about that. When I was working on Orion, dealing with a large solar event was an issue for the design of the crew capsule. I don't know what the final situation was. I know that they were supposed to test the solar storm shelter on the Artemis 2 mission, but did not do it for various reasons. But the concept we had for initially in Orion was to carry along basically plastic panels. Plastic is very good at stopping, hydrocarbons are good at stopping solar radiation events. And you would put panels, they would build basically inside the capsule a little huddle, a room where the four crew could huddle inside it for the few hours to let the event pass. Think of it as trying to put four people into the old style telephone booth or a TARDIS, if you're a Doctor Who fan. And they would be inside there during the solar event. Plus, you would position the Orion tail first towards the event. For the lunar surface, they talked about having the possibility of a storm shelter inside the crew the crew habitat. Also, you can do a certain amount by positioning equipment at the top so that it block where the sun's coming down or on the sides. So a combination of equipment and probably some deployable panels was one thing that was kicked around, like was being considered for Orion.
The second question I have, and I will quit after that, is about the temperature. And I got very much concerned about the what do you call thermal cycling. And this hit us hard on Skylab. In fact,
Mhm.
we lost one experiment after six, 90 days
Mhm.
because of thermal cycling. You have 350 degrees Fahrenheit plus,
Right.
then you can get into minus 200 or so degrees Fahrenheit. Was that addressed for these habitats, this thermal cycling, how that affects the entire uh, everything.
Yeah, I'm sure it was. I had a kind of I was kind of off to the side. I didn't, the meetings were kind of, they had teams looking at all those things. They were looking at using space station designs for the HAB and HAB module. So I'm sure that whatever they were planning on doing for space station was they were going to end up doing for this. I had kind of I was kind of off to the side in this automation and robotics group. We got brought in a little bit late. They'd already started on a lot of the work and had a lot of the meetings before we were brought in. So I don't know all the details, except what I saw in various mass presentations, like what these slides are from.
And
I'll say,
Edmund, I
yeah,
want to add what Dr. Kumar was asking, and
yeah,
especially in parallel related to the experiments that he was
yeah,
involved. They were going about at the same time or probably even after the
yeah,
time frame that you are
right,
using materials from. So
yeah,
Dr. Kumar, that you have a little bit different perspective, and I think your teams were looking at the some of the solutions that stemmed from those the brainstorming that happened at the meetings that Edmund is drawing his presentation information.
yeah,
I may have seen, been in some of his presentations. The
yeah,
last thing I got to tell you, and that's why I have your email address.
huh?
I was so concerned about this lunar dust because I talked to Buzz Aldrin, I talked to several astronauts, including Captain John Yang, and they told me, Kumar, concentrate on this thing. I couldn't. I raised my hands on the moon, but
Yeah.
then I kind of wanted to focus something, and that's the paper I'll send you. I wanted to
Okay.
focus the attention of everybody on this dust, right? So I did a clever thing. I developed a mathematical model for a dust particle in a Mars dust storm. It was kind of trivial,
Yeah.
not so trivial, but that brought up this situation, and then we put that challenge on the uh, NASA at work, etc. I'll send you that paper, but
Thank
that
you.
paper concerns itself with my entire life, uh, professional life, learning about exponential functions. And this is the question I asked Bob Curl. Bob, here everything is modeled as exponential functions. We were going together learning about these nanotubes, and Bucky, while I'm laughing, he looked at me. He said, Kumar, let me think about it and I will call you back. He never called back. Thank you very much. And I got your email. I'll send you this paper.
Thank you.
I hope you will enjoy.
Well, well, I have a question,
Yeah.
probably for Dr. Kumar more than anybody, but I think the dust on the moon is much more of a problem than the dust on Mars. The Mars dust, I think, is doesn't have those jagged edges. It's more rounded, and that's probably because of the weather on Mars. And what about asteroids? What are the dust like? What's the dust like on asteroids? Have you got any idea about that,
I don't, but
Dr.
I'll come back to the Mars dust. It can change your trajectory. It will fall on everything like your solar panels, etc., because it's a moving dust and it has happened to us. It may not be as dangerous as the dust on the lunar dust. That's why I washed my hands off of the lunar dust because one astronaut said, Kumar, I saw something raising up. Now, I have spent a lot of time in this electromagnetic research. That's not so trivial. He said, I saw something raising. Man, now you got to cope up with another problem. Although it's vacuum, but this dust can raise up because of the electrostatic
Mhm.
repulsion. So I was laughing. I said, no. But my idea about the Mars dust is going to be very detrimental because of its moving, attribute. It moves, it has 7 to 12 or something like that kilometer velocity. It can change your trajectory. It can do a lot of damage to you. It will settle down on everything, etc. I rest my case. I don't know much about it, but I wanted to just kind of kick off everybody's thinking into dust, dust, dust. And
Yep.
I did my thing. And I will send the paper to Svetlana also if she wants to distribute it. She is most welcome.
So we
Right.
don't know
And
anything about
also
asteroids, do we?
for everyone, that dust, when we think about dust, very often people have in their image drawn as dust bunnies and something fluffy and so on. That terrestrial dust. Dust on the lunar surface is different, and dust on Martian surface is going to be also different with different properties. So right now, let's focus on lunar surface because that's the focus of this presentation. And Mike, do you have a question for Edmund?
Well, I had another question, and that was since Golden has left and come back and we have a different administrator, um, is there any additional considerations for robotics and for AI use on the on establishing a lunar base?
Very, very much so. We had a Gateway event the other day, kind of a farewell to Gateway since Gateway is paused. They didn't want to use the cancel word. Um, the One of the things they're doing as part of this ignition event, I don't know how much if you've seen that, but the new administrator wants to move things at a very rapid pace, similar to what was done during Apollo. If you look at the launch cadence during Apollo for manned and unmanned missions, it was extremely fast. And he believes that with the current launch capabilities that have been developed by SpaceX and others, we can accelerate what we're doing. And the original plan for the lunar rover was for the Lunar Transport Vehicle, LTV, was one rover that could carry the crew and work for a certain amount of time, would be teleoperated, have the capability to have a robotic arm placed on it, to be operated from Earth or from the base, from the lunar surface. But they're now going to deploy a series of inexpensive, less capable rovers for characterizing the landing sites. So there's going to be rovers that'll be operated from Earth. Probably some of them will have robotic capabilities to do characterization of the surface. They're looking at, how can we manipulate regolith to make protective berms, maybe even put it over some of the habitats. So a lot of that is site characterization and characterization of the lunar dust properties at the poles. The South Pole is a big emphasis. I will say AI is an issue, is a hot topic inside NASA. They've deployed the Copilot large language model to people that want to use it in a secure fashion. And there's a strong emphasis on some of that. I mean, I did AI research back in the 1990s when expert systems, rule-based systems were all the rage. And what they've got now with the large language models is very good. The area in AI that's probably the most advanced and will have a utility for the moon, I think, is image processing and image understanding. There is, I work for Booz Allen Hamilton, and there are substantial programs inside Booz Allen for some of the security agencies and intelligence agencies that is deploying AI all through it to do natural language understanding, image understanding, and also it's definitely something NASA is looking at. Constraint is going to be processing power. And one area that may help is Booz Allen and HP deployed a space station payload recently. I think it was about a year ago, where they put one of these large language models onto the space station that had maintenance information in it, so the crew could ask it questions about maintaining space station equipment. So we have a question in the chat on operational lifespan. How many missions before replacement? And would the replacement be deployed at the same or different site? I don't know what the full lifespan was supposed to be. I don't think I ever saw that mentioned, but certainly several missions could be done to the same outpost. And replacement, that was when I showed that waypoint slide where they were going to have several different alternatives. One alternative that was considered was deployment of an outpost on the far side with a communications relay satellites. There's an area on the far side that is one of the geologically oldest regions known in the solar system. It dates probably back to right after the creation of the moon, and that's of extreme interest to the geologists. I know that was one of the sites they had the Artemis 2 crew spending some time looking at and photographing. So it's far side was one of the potential options down the road. Oh, payload return. Let's see. I think it was on the order. It was like 100 kilograms or less. I know one of the big things now that the geologists want for return of samples is for them to be refrigerated, freezers, so that any volatiles trapped in the like regular samples from inside the permanently shadowed regions, they want those kept cold so that any volatiles inside can be studied. And also, yeah, that was what was planned. I can take one or two more questions. I have a personal business I need to attend to in a short time. Any further questions?
I think we're good, and I want to thank you for presentation. Thank
Yes.
you for attending.
Edmund, I sent you my paper. Sorry, Svetlana, I sent you my paper in the email.
Great, thank you. Thank you.
Yes, and I also want to thank everyone, all our community, for supporting, joining this early in the morning on Saturdays, and having this both attentive discussion and questions that stem from it as we are approaching next cycle of exploration and establishing our presence on the moon. It's going to be lots of challenges, as you see with the lunar dust is one of them, but there's many other challenges that we may or may not mention this morning. And everyone's thinking power will be extremely important, and contribution will be valued. Thank you very much, and please attend next Saturday. We'll see you.
Thank you, everyone.
Have a great day. Have a
Thank
great
you.
weekend.
Outstanding
Thank you, Edmund.
presentation, Edmund.
Thanks.
Thank you.